Hello everyone, today I will present our work VindLU, a recipe for effective video and language pre-training. Video and language pre-training is expensive to train and has complex architectures. Our goal is to make video language pre-training more efficient, effective, and accessible. We start with image and text encoders, trained on video text pairs using a contrastive loss. We then progressively add more components while studying the importance of each component. Using our empirical insights, we then develop a step-by-step recipe for effective video language pre-training. Our final recipe outperforms the original baseline by 23%. It also achieves state-of-the-art results on 9 video language benchmarks. Here's the details. Video and language pre-training aims to enlarge the representations of video and text on large-scale video text datasets. Once a model is pre-trained, it can be applied to many downstream tasks, such as text-to-video retrieval and video question answering. This scheme has been shown to be very effective for downstream video language tasks. To build the recipe, step 0 is our simple baseline. We use a VIT base as the image encoder and the BERT as our text encoder. The model is pre-trained with the video text contrastive loss on width 2 million video text pairs. After pre-training, we fine-tune the models on 3 downstream datasets and report the average top 1 accuracy on these 3 datasets. The image transformer baseline achieves 50% accuracy. Step 1 is to add temporal modeling. Temporal modeling aims to aggregate the information from multiple frames. It has been shown to be very important in action recognition tasks. We tried 4 different temporal modeling methods: mean pooling, late temporal attention, temporal convolution, and temporal attention. We can show temporal attention outperforms the mean pooling by about 6%. Step 2 is to add multimodal fusion encoder. The purpose of multimodal fusion encoder is to fuse multimodal cues from video and language. We tried several implementations of the multimodal encoder. The V2T multimodal fusion is to inject video information into text by cross-attention. The T2B multimodal fusion injects text information into video. And the bidirectional multimodal fusion combines the V2T and T2B. The results show that the V2T multimodal fusion leads to about 4% improvement, but the T2B multimodal fusion is not necessary. The step 3 is to investigate how important each pre-training objectives. Video-to-text contrastive loss aims to maximize the score of paired video text and minimize the score of unpaired video text. The second is the masked video modeling loss. 50% of the patches are masked, and the target is to predict the masked patches. The third loss is the video-to-text matching loss. Its target is to predict whether the given video and text is matched or not. The fourth objective is masked language modeling. 50% of the words are masked, and the target is to predict them using the video and unmasked text. This table shows the results. BTM and MLM objectives lead to a significant improvement, 4% and 6% respectively. The improvement from MVM is only 1%, which is a bit marginal. We also investigate the pre-training data. Training jointly on images and videos led to more than 3% improvement. Pre-training on 4 frames is sufficient, and provides large reduction in the computational cost. Third, multi-stage pre-training is not necessary. We investigate the number of frames during training and inference. Fine-tuning on 12 frames provides a good trade-off between accuracy and cost. Another interesting finding is that even the model is fine-tuned with 12 frames, inference with more frames yields to slightly better results for larger computational cost. We also scale up the training data and model size, both lead to a substantial improvement. Our final recipe outperforms the original baseline by 23%. We compare with the state-of-the-art methods on text-to-video retrieval task. VindLU outperforms the current state-of-the-art by 7.8% on DiDeMo and 6.1% on ActivityNet. Something to something V2 label and something to something V2 template are two temporal heavy text-to-video retrieval datasets. VindLU also outperforms previous SOTA by a large margin. On video question answering task, VindLU achieves competitive results across many video QA datasets. In action recognition, VindLU outperforms Transformer and OmniVidL by 2%, 1.1%, and 1% respectively. In conclusion, we demystify the importance of various components used in video language framework design. Second, we provide a recipe for building a highly performant video language model. Third, our model achieves state-of-the-art performance on 9 video language benchmarks. Thanks for listening.